Yeah. And it makes sense.
Hey, can we do the question that has like 6 answers on it?
Oh, yeah.
Yeah.
Because I don't know how to do that.
Which, yeah.
It's like, it gives you like the pyramid with the bisector and stuff.
Ask for like measure 1 and 2
And it's like, it's
Oh,
supposed to be
okay.
like angle 1, 2, 3, 4.
Yes, we'll look at that one. Don't let me forget. Don't let me forget. Okay, so a couple things from section. Really, we're only going to do probably 4 sections from chapter 5. First one we already talked about, at least most of it. It had to do with segment bisectors and angle bisectors. And so what we've got here, this quick review, we already kind of went through this, but it's been a few days. So we've got this segment, this red segment AB, and it is being, the blue line is a perpendicular bisector of the red segment. To prove that, we can prove that. Let's move these things around a little bit. Look at these 3 pieces of information up here. It tells us that AC, the measure of AC is 5.5912, measure of BC is 5.5912. So that's telling us, isn't it, that AC is congruent to BC, right? Everybody agree? Okay. It's telling us that the measure of angle ACD is exactly 90 degrees. So that's telling us that the blue line and the red segment are perpendicular, right? So everybody agrees then that the blue line is in fact a perpendicular bisector of the red segment. And it stays that way. If I tweak this thing a little bit, all those measurements still retain those relationships, don't they?
Yeah.
Right? Okay, so then what do we got here? Well, point D is just some random point on the perpendicular bisector, right? I can drag it around, and as I drag it around, some things change. Let's look at what changes here. Well, the length of AD, which represents the distance from point D to endpoint A, and the length of segment BD, which represents, the length of D from this other endpoint. Notice what happens. No matter what I do here, what happens to those measurements? Those who are sitting up front can see it. They stay the same, don't they? Right? So there's a visual representation of the first part of 5.1, the perpendicular bisector of a segment. We know that if a point, in this case point D, lies on the perpendicular bisector of a segment, then what has to be true? What has to be true of point D?
Equidistant from the endpoint being me.
Yeah, it has to be equidistant from the endpoints, right? Same distance from the endpoints. No matter what, it always will be, right? And so we know that if we could turn that around and say, okay, well, if the length of BD and the length of AD are equal, then we know that D must lie on what? The perpendicular bisector of that segment, right? Because the perpendicular bisector of the segment, that whole blue line, that represents all of the infinite points. The infinite points that are equidistant from the endpoints A and B, right? And D just happens to be one of those. Okay? There are some other relationships that maybe we could find. Like if we look at something like AC and BC. Well, what do you notice about those two? Let me separate those two a little bit. What do you notice about those two? People sitting up front. They're the same, but that's duh, really, right? I mean, that falls under the category of duh, because they have to be. We know that point C is the bisector of this segment, and what does it mean to be a bisector? Cuts it in half, right? Okay, but when we start looking for other relationships, like if we want to look at, for example, the relationship between AC and maybe AD. Now watch, so here's AC, and here's AD. Watch those two. What do you notice? AD is changing, but AC or CA is not, is it? Right? So what's that tell you? Is there a definite relationship there then?
Oh, no.
There can't be, can there, right? And even if there, in some cases where there might be a definite relationship, let's measure something like CD. let's compare CD to AD. And they seem to be changing, don't they? If I go really far away, so they start to look pretty close, don't they? Do you think that CD is ever going to catch up to AD? And can't, can it? It never can, because think about this now. So think about this in terms of a right triangle relationship. If that's a right angle, then this is a right triangle, and that's the hypotenuse, right? And the hypotenuse is always the longest side of a triangle, right? So it's never going to catch it. But we notice something kind of important here. We notice that as we move this thing around, that relationship seems to not be very consistent. Because now as D gets closer to C, look at these distances. Now CD is quite a bit smaller than AD, and if I go clear down here, it's a lot less than half, right? So do you think there could be a relationship there? Doesn't seem like it, does it? There's not some kind of a fixed relationship there, right? Does that make sense? Those are the kinds of things in geometry that I think it's important to, and that's one of the real values of a geometry class, is that I think it helps you to get to a point where you can kind of visualize things a little bit. And you kind of want to try to play this simulation in your mind even sometimes. I know you don't always have access to this fancy program, but you can still think of it in those terms. If I were to tweak this triangle, would there be some kind of a relationship that would hold up? No, there's not. The only real relationships here are that these two things are equal, right? That's the only new thing we learned. Everybody see that? Okay? That point D is equidistant from the endpoints. Okay, let's look at the other part of this here. So here's what I've done. I've created, maybe I wonder if I should walk you through this. You know, I'm going to. I built this one, but let's go ahead. I just want to kind of get you used to making these sketches too. You're going to do more of this. What if I want to build an angle bisector? Okay, there's some ways to do this quickly using Geometer Sketchpad or using the one that you have access to, like the free one you have access to, this GeoGebra. They were very similar kinds of program. So I can create, let me make a ray. And start there and make a ray. Okay. Let's make another ray. Okay, and those rays create an angle, right? Okay, so let's go ahead and bisect this angle. We can do that. If I, whoops, I want to do that. Okay, if I just highlight this side of the angle and the vertex and that side, I can construct a, maybe I have to have, I think I have to do this. I think I have to do that. I think I have to highlight those 3 points. And now I can construct an angle bisector. There you go. Okay, make sense? Let's kind of color code these a little bit. Let's make that middle one so we can talk about it in terms of color. Let's make the middle one green, and let's make the bottom one, how about red? Oh, oops. There we go, okay? So what we want to do, we've got this perpendicular bisector. We can prove that because I can measure these angles. Let's go ahead and highlight these points, and I'll label them. So we'll label the points. We've got point A, we've got point B, and we've got point C. Let's put another point on this bisector. So I'll construct a point that's on the bisector. Now by doing that, when I construct a point that's on the bisector, I can drag it around, but I can't drag it off, right? It stays on the bisector. Okay? Let's label that one too. Okay, so let's measure these then. How about if I measure angle A, B, C? Measure that angle. There it is. Let's measure angle A, B, D. What do you think is going to be true? How's it going to be related? It'll be half, isn't it? Should be half. And it is, right? And then let's measure angle C, B, D. How's that one related to? So, okay, good. It's the same as ABD, isn't it? Okay, and they are. If I tweak this a little bit, let's make this something, try to make it more of a round number. Well, it's close to 46. So these are real close to 23, right? Okay, now what we want to do is I'm going to take maybe this point D, and I want to define a distance from point D to each of the two sides. Okay, to do that, let's talk for a second about the distance to a line. Okay, so here all I've got is this green line, and I've got this point A, and I dragged out a circle, right? Think what a circle really is. A circle is really just the set of all the points that are the same distance from A in a plane, right? If an ant started at the center of this at point A and walked in a straight line out to the edge of the circle, he's going to walk the same distance to the circle regardless of which direction he takes, right? Everybody agree? Okay. So we can measure this distance. Let's say here's the distance from A to B from the center to the edge of the circle, and it's about 8.4513, blah, blah, blah. But I asked Geometer Sketchpad to measure the distance from, A to the line, and it told me something different. It told me a distance of 6.8384. So it's telling me that the distance the ant walks to the line, if he walks the shortest distance, is less than the length of that blue segment. That kind of makes sense though, doesn't it? Right? Everybody agree? If the ant were going to take a more direct route, what would he probably do? Probably aim somewhere between those 2 points, right? If he aimed in this direction, he could get there more quickly, couldn't he? Right? Well, let's take a look also at the measure of this angle A, B, C, okay? The measure of angle ABC right now is like 54 degrees. So the ant should always aim in between those 2 dots though, shouldn't he? To find a more direct route. Well, look what happens if we drag these closer together. What's starting to happen? He still should always aim between those 2 dots, shouldn't he? Right? But as those dots get closer and closer, the radius of the circle is starting to match up more closely with the distance to the line. When are they going to be equal? When would the radius of the circle be exactly the same as the distance from point A to the green line? What do you think is going to happen to these measurements? What do you think the measure of that angle is going to be? It's going to be 90, isn't it? Let's just verify that. So if I drag these to the point where the 2 dots exactly overlap, I can't quite control it that precisely, but it's pretty close. Oh, why is it doing that? Can't quite get it there, but it's close. Come on. Oops. That's probably about as good as I can get it. Okay, well that's pretty close. It's trying to be 90 degrees though, isn't it? And when it's about 90 degrees, when it's exactly 90 degrees, look at those distances. The radius of the circle, AB, is equal to the distance to the line. So that just reinforces again. There's kind of our visual version, our visual explanation of when we talk about the distance from a point to a line, we mean the perpendicular distance, right? That is the shortest distance. Everybody agree?
Yeah.
Okay, we just saw it. Okay, so we know that's true. Now let's go back to this guy. Okay, so if I want to measure the distance from D to the blue side of the angle, I'm going to measure a perpendicular distance, aren't I? Right? So let's do that. Let's find the distance from D to, oops, gotta highlight just D there. Let's construct a perpendicular line, how about? And let's make it a really light color, and let's make the line really thin. Okay, so there's a perpendicular. Now let's find the point of intersection. Right there. And let's label that. So that's point E. Let's do the same thing down here. Let's find perpendicular line, a line that's perpendicular to D and the red line, or through D perpendicular to the red line. Okay, and let's find that intersection. And let's label it. And that's F. So what do you think here? Can you hypothesize anything about this? I'm looking specifically, I want to look at this distance from here to there. So that's the length of segment ED and the length of segment why did I do that? There. Better. Okay, and the length of segment FD. What do you think? They're going to be the same, aren't they? Okay, you can kind of see it in the picture, but let's see if that's always true. Maybe if it's true for just that one point. Let's measure those. So if I measure ED, that distance, and we measure FD, they're the same, aren't they? What's unique about D? What's the only thing? How did we define D again? What is it? It's a point on what? On the bisector, right? It's just any point that's on the bisector. That's the only thing it has to be. I can slide it anywhere I want to as long as it stays on the bisector. But no matter where I slide it, look what happens to those distances. They stay the same, don't they? Right? So what's that tell us? If a point lies on the bisector of an angle, then what? How would we say that? That this distance is, that it's equidistant from what? What do you think? Tyler, get an idea? Yeah, you can do it. Finish my sentence here. If a point, D, lies on the bisector of an angle, then it's equidistant from what? What would I call those things? Yeah, the sides of the angle. That's it. You got it. Right? Then it's always equidistant from the sides of the angle. Okay? And so we could turn that around and say, if a point is equidistant from the sides of an angle, then it must lie on what? What is that green thing? The angle bisector, exactly, right? Okay, so we got a lot of stuff there, right? So we showed that these are congruent. We've got quite a bit of stuff we could mark up now on this drawing, because we know that we just showed that those are congruent, right? They have to be. And by definition, those are congruent because the green line is an angle bisector. We know that what can you tell me about the angle between the blue and the purple, or the red and the purple? What's that angle have to be? It has to be 90, doesn't it? Because we know that the distance from a point to a line is always the perpendicular distance, right? So we could make that a right angle and that a right angle. Is there anything else that we get for free? Any other congruence information we could add? What do you think? Should I hide? Is this getting a little... Here, let me hide some stuff. How about if we go... Oops. Let's hide this and that. Might help a little bit. So now we're just looking at kind of this triangle and this triangle, aren't we? Any other information there? Mark, you see anything else that I could say is congruent between the top triangle and the bottom triangle? The hypotenuse, they share a line, don't they? Good. They share a side. So we could say this is true also. Whoops. We could say this is also true, right? They share that side. And so now we're trying to show, can I say that, my goal is I want to say that the top triangle well, let's call it EB, I guess we need that point. Oh, there it is, never mind. Over there. So triangle EBD is congruent to, what triangle does it look like it's congruent to? How would I have to label the bottom one? Yeah, I'd have to, F corresponds to E. If I folded them over, those would overlap, right? So it'd have to be FBD. That's what I want to say, but what's my justification? Do I have some triangle congruence relationships that support that? Can I use any of them that are just work for all triangles, like using S's and A's? You see any? Angle side works, doesn't it? Right, if I walk around like this triangle in this direction, if I start there at that angle, and I walk around like so, I hit angle, angle, side. Same thing down here, angle, angle, side, right? That works, doesn't it? Okay, so there's one. So I could use angle, angle, side. Any right triangle relationships, the ones that use H's and L's and A's. Let's label the parts of these as right triangles. So let's see, for this top triangle, the green side is what? That's the hypotenuse, good. So that's an H, it's also an H for the bottom. Then these must both be legs, right? And then these are just the acute angles. So that's an angle, that's an angle, that's an angle, that's an angle. Well, look what we get here. We get lots of combinations, don't we? So what's one that would work? Where do we have congruence marks that would work for a right triangle relationship? Hypotenuse leg would work, because I've got a hypotenuse and a leg congruent to a hypotenuse and a leg, right? So we could use HL. What else could we use? HA, hypotenuse and acute angle. What else? I could do leg angle. I could do, I guess I can't quite do leg, can I? But I could use any of those would all work, wouldn't they? And then once I show that the triangles are congruent, then I know that all the other corresponding parts have to be congruent also. So I get to add everything else, right? So look at all this stuff we have. Now we've got this side corresponds to that side, so they're congruent, and then I know that this angle corresponds to that one, so they're congruent. So there's a ton of stuff, right? There's a lot of relationships here. So what's the relationship between segment BE and segment BF, for example? They're congruent, so their measures are equal, aren't they? Right? So on Moodle, if you got that question, they wanted to know BE is related to BF. Well, they're equal. It's not an NA, is it? I mean, they're equal, right? Does that make sense? Okay? All right. So, question came up. Okay, it was which one? The one that had a. Oh, I know which one it was, I think.
No, the question is the ones that say that the angle is one I had. What do we call that?
Yeah. Okay, so I think this is the one. Yeah, find it here.
Right here. From this morning?
Is it not back?
Okay, so help me find this. Was it towards the end?
I think it's like 12, 13, 14.
Okay.
Yeah.
No, 13.
14.
14.
Yeah, like that one. Okay, yeah, let's look at that one.
Really?
Yeah.
Ooh, that looks terrible, doesn't it?
Yeah, it's terrible.
No, it's easy. You don't think it's easy, or
Only thing I was thinking it would be like.
Okay, hold. Let's have a look here. Okay, what are you thinking, Makai? What are you thinking here?
The only thing I was thinking would be like.
Listen, please.
I was just thinking like alternating two and stuff like that. But I didn't know.
Okay, yeah, well, okay, so on this one, phones away, please. Okay, all right. So, yeah, so we can't really use alternate interior because that's the stuff that, in alternate exterior, those, remember how those all work? Those are the ones that are related to parallel lines being cut by a transversal, and we don't really have parallel lines here, do we? So what's gonna be probably the most important relationship here? Triangle sum theorem, right? What are the sum of all the measures of the interior angles is always? 180. Okay, so then it's gonna be a matter, and this is a perfect example to illustrate why it's so important to just kind of fill stuff in, right? To fill in the blanks as you go. So we know that if x is 44, I'll get you going on just one little hint on this. So if x is 44 and y is 53, well, that's not enough really to kick us free with, well, I guess it actually is. We know a couple things. If that's a right angle, isn't that a right angle? So I should be able to know what angle 1 is then, shouldn't I? Right? And if I know 1, I know 2, and then it just starts to snowball and things start to fill in a hurry. Okay? Make sense? Okay, good. Okay. What's that?
It's the one that says, like, it has 3 letters, which equals 2 letters.
Okay. Let me keep going.
It's like, no, it's behind that thing. It just,
Oh, further back?
it's like 11 or 12. You should just come up and get help. Hey, that one. Yeah, that one.
Okay. Okay, real quick here. I'm not going to give you too much help on this, but listen, please. Okay, so the key piece of information here, this is the part, and this relates to that discussion we just had. If F is on the bisector of angle DAE, so here's the angle DAE, right? So this is the bisector of that angle, and if F is on that, then we should know some stuff, right? We should know some stuff. So angle, well, this is actually a pretty easy one here, because if EAF is going to be what?
It's going to be half of the thing.
45.
Yeah, it's going to be,
45.
oh, you know what? Oh, never mind. That didn't give you what you're supposed to know there, did it? What?
Yeah, see, this one kind of confused me because I just
Okay,
put.
because the question, no, okay, yeah, so that's, the question is supposed to give you a number there. So I gotta go in and fix the question. It's not supposed to say DA, that's supposed to be that's in my programming language, that's supposed to be. So I messed it up. I'll go fix it.
Okay, can we get comments out now?
How many people are done with this assignment? Everybody done?
Yeah, it's just that question.
Just that
I
question?
didn't even have that one on mine.
Okay. Okay, then. Oh, we have a lot of time, don't we?
Yes, yeah, we finished the test.
What the heck?
We get out at 11:05.
Oh, never mind. Okay, we don't have a ton of time. Okay, 15. There's one more. I'll fix that problem. This section, we're only doing 4 sections in chapter 5. This is the second section, and it's really simple. There's only one relationship that this section focuses on. So, shop it away. You got to pay attention to this. So, we've got this big triangle ABC, right? What I've got here is I've got the 3 midpoints of each of the sides of the triangle are up here. So D, E, and F. And notice when I tweak this thing, the midpoints always stay the midpoints, right? Everybody believe me that D, E, and F are the midpoints of the 3 sides? Okay, because they are. Okay, now what I want you to do, I want you to just see if you can predict some relationships. What we're trying to get here, we're trying to get some relationships between what we call the midsegment. The midsegment of a triangle, there are 3 of them, but the midsegments are just the segments that connect the midpoints of the sides. So we've got one of the midsegments up here. This midsegment connects points D and E, which are each midpoints of the 2 left and right sides of this triangle. So watch me tweak this thing a little bit here and see if you can, do you notice anything happening here between the red line, and I'm gonna go ahead and label this one, how about green for a second? So do you notice anything about the red and green lines? Okay, they seem to be parallel, don't they? Right? They seem to be parallel. Well, let's just check that and see. What's a way that we could show that they're parallel? What's a test I could use up here? Are there any angles I could measure that would tell me if they're parallel? Say it again. Okay, how about measure angles A and D right here, right? So let's measure those and see. So I've got angle CAB is this upper angle. Let's measure that. There it is, 69.7808. Now let's measure angle EDB. Oops. EDB. What do you notice about those if you're sitting in the front? They're the same. So if those angles are the same, those are corresponding angles, aren't they? Right? If corresponding angles are congruent, then the lines have to be parallel, don't they?
Yeah.
Because I've got two lines cut by a transversal, right? So that's one thing we know. The green and red lines are always parallel. Okay, so that's true. The mid-segment is parallel to the opposite side of the triangle, right? Okay, what else? What about the lengths of the green and red sides? Any suggestions?
It's half.
Let's find out. Is it half? It looks like the red one seems to be about half. So let's measure. The measure of AC, there it is. And there's DE. Okay, let's try. I'm gonna try to get one that's close to an exact, whole number. I won't be able to get it exactly, but pretty close, right there. So this is just a smidge over, to use a technical term, just a smidge over 12, and that's just a hair over 6, right? So they are. It appears that they're about there's a 1 to 2 relationship there, right? The mid-segment is half as long as the opposite side, and that always seems to be true, right?
Yes.
Okay, that's it. That's the mid-segment theorem. That's what we know. You don't really need to know anything more to do the next assignment, so grab a Chromebook.